Thank you. My name is Zourmpakis Alkinoos, and I will be presenting the paper, The Development of Computational Thinking through Adaptive Gamification and Learning Analytics to Enhance Science Education. And so basically, we were going to see two things. One is a TPACK-Based professional development program for teachers, specifically pre-service teachers, and the adaptive environment methodology, which we are following. I am a postdoctoral researcher at the University of Thessaly. Okay, this is the content. Forward. So, what is computational thinking? Computational thinking is a fundamental problem-solving skill for the 21st century and is considered as essential as reading, writing, and arithmetic. It is not simply thinking like a computer. It is structured in a way for people to solve complex problems. A definition that we can give is basically the mental processes involved in formulating problems and their solutions so that those solutions can be represented in a form that a computer or a human can effectively execute them. Now, what is the importance of computational thinking? It has become apparent, especially in the AI era, that digital competency and CT skills are as fundamental, as I said, reading and writing. But that's not just for the computer scientists. CT skills can enhance problem solving, critical thinking, creativity, and perseverance. So it's not something just for basically those programmers. Naturally, CT is increasingly integrated into K-12 curricula globally, as it can equip students to navigate and participate in the increasingly digital world. It is recognized as an effective tool for analyzing and solving problems across many disciplines, particularly in math and science education. Now, especially regarding science, education, and STEM, it can provide a foundation for inquiry and problem-solving processes. So, when we talk about computational thinking, it is vital to understand that we are moving far beyond just teaching students how to program. Instead, CT acts as it can act as a powerful cognitive tool for scientific inquiry. The logical structural processes inherent in CT naturally mirror the scientific method itself, such as observe, hypothesize, test, and revise. By integrating these concepts, we transform the science classroom from a place of passive observation into an environment of active analytical exploration, equipping learners with the mental frameworks, basically, they need to systematically approach complex scientific phenomena. Now, so basically, we know that the CT is a crucial cognitive tool, but how we teach it also matters. The traditional one-size-fits-all approaches often fail because they cannot accommodate diverse learning paces or needs of the students. To bridge this gap, our methodology first looks at two powerful concepts. First is the adaptive learning, which uses algorithms to personalize the educational pathways based on performance and choices. And the second is gamification, which basically taps into to keep learners engaged and uses game elements to increase motivation. However, the true breakthrough in a way is when we combine these two. Adaptive gamification doesn't just personalize the difficulty of the content, it tailors the motivational delivery itself, creating a highly responsive and individualized learning environment. So in other words, we can dynamically alter both instructional content and motivational mechanics in real time. Despite the promise of this technology, there are practical implications that we face. The most main one is the teachers themselves. Currently, there's a lack of specialized K-12 teachers who possess prior city knowledge or the confidence to utilize it in teaching. Furthermore, the role of the teacher is evolving towards providing strategic support for self-directed learning. So to help teachers, and especially pre-service teachers, navigate this transition, we cannot rely on standard technical training. So another tool that we utilize here is learning analytics, which is basically the measurement, collection, analysis, and reporting of data about the learners and their contexts. So by tracking data, the teacher educator can monitor progress in real time and provide precise support exactly when trainees encounter misconceptions or obstacles, while minimizing students' frustration. So, to address all these challenges, our architectural framework relies on three main pillars. First is the core build, which consists of a custom adaptive gamification environment. Here, the players or the pre-service teachers interact with a system where game elements and learning is being adapted to their specific needs and motivations according to the Hexad player type and their actions. The Hexad typology, which we're going to see later, is a player model that is based on self-determination theory, which is basically a motivational theory. The second is our pedagogical strategy that utilizes a combination of problem-based learning and a play, modify, create approach, allowing pre-service teachers to deeply engage with and manipulate the concepts. Finally, all this is supported by the learning analytics system. So basically, we have a parallel learning analytics dashboard, which collects real-time data from the player sessions, and teacher educator basically, to make informed decisions about and how to intervene to provide accurate and on-time support. Now, in order to make a little clear how the Hexad typology works and how our engine works, here we will explain how we do it. So basically, when you enter the application, the users will complete a 24-item questionnaire, which is entirely based on the Hexad typology. The system then analyzes this to find their dominant motivational profile, while also accounting for secondary traits from other user types. Basically, the second and third in categorization. Then the Hexad typology categorizes users into 6 types. And this means basically the dominant type, which we have the achievers, who want mastery and challenges, players who are motivated by extrinsic points, philanthropists driven by a purpose to help others, disruptors who want to test boundaries, and socializers who are motivated by narrative and interaction, and I forgot, the free spirits who crave autonomy and open exploration. So the adaptation process is highly dynamic and unfolds across 3 distinct layers. First is the initial configuration. We have the interface and the reward mechanics that immediately align with the user's dominant Hexad type. For example, an achiever sees a UI focused on badges, while a socializer sees minimal interface, mainly by prioritizing the narrative, the story. Second, during gameplay, the system tracks time, mistakes, and the interactions with the NPCs, which means non-player characters. Finally, if the student struggles consistently or progresses too quickly, the system triggers changes in game pacing or and, depends, changes in game mechanics. For example, by providing indirect hints, removing any assistance, or even giving direct guidance, ensuring that in that way the challenge level remains engaging and or the choice of the player heard. So, a major innovation in our system is the integration of AI NPCs. These are not traditional characters with static dialogue trees, basically, and they act as intelligent scaffolds. They serve two primary functions. They act as assessors who evaluate the user's problem-solving logic, and they act as natural language feedback providers. For example, an AI NPC can gently guide the users toward a better solution if the first attempt fails. Currently, we have basically linked the NPCs with the Gemini 2.5 Flash model via API. The reason that we use Gemini is because we utilize the Unity, we have built the application through the Unity 3D game engine, and it can be directly linked with Gemini more easily. However, to eliminate third-party data risks and ensure absolute data sovereignty, our future framework proposes to in deploying open source models directly on local university servers. We can talk about that, like the DeepSeek Qwen 2.5 or Gemma 2. We can talk about that later if you want. Now, we can look at the practical application of the curriculum. We intentionally sequence the learning starting with conceptual tasks entirely unrelated to programming. We begin with a peanut butter and jam sandwich activity, where users must instruct a hyper-literal, in a way, AI NPC to how to make a peanut butter jam sandwich. This will highlight the need for precise steps. From there, we move into problem-based modules that explicitly link to science. For example, for the concept of abstraction, users plan a party by filtering details, which will later directly translate in the science teaching. For example, in using standard abstract symbols when designing electrical circuits. For decomposition, they will design a treasure hunt route, which teaches them how, later in the science learning, how to, for example, troubleshoot a broken mechanical toy by testing it part by part. Now, in pattern recognition, the players will engage with puzzles to identify logical patterns, which will then bridge to scientific observation. For example, having to analyze shadow lengths at different times of day to recognize solar movement. Finally, regarding algorithmic thinking, the users will define strict if-then logic for everyday decisions, like morning routine. We connect this directly to science experimental design by showing teachers that a valid experiment requires a strict algorithm, such as changing only one variable at a time when testing a toy car speed down a ramp. In the picture, we can see it's basically an alpha model of our application. And it's also in Greek. Now, a vital part of this entire process is the learning analytics dashboard. While the pre-service teachers are engaging with the gamified gamification app, the instructor monitors the real-time progression, mistakes, and the player types. From a technical standpoint, the Unity 3D client sends serialized data via Firebase directly to the UI on the instructions tablet. This is another reason why we basically use the Gemini, because Firebase is also Google affiliated, so we have a very sufficient, like, it works easier and faster the moving the data around. So this isn't so basically all this the learning analytics is not just to track their grades, but to allow the educator to tailor their in-person interventions. For example, if the dashboard shows that, which can happen, that the room is full of achievers or player types, the instructor can deliberately use more competitive phrasing to maximize engagement, for example. Or if a player has stuck on a mistake, and the instructor can see what he keeps answering and figure out a way to help him, not indirectly. Now, all of this technology is deeply embedded program within a professional development program grounded in the TPACK framework. We want to ensure that we don't just isolate technical training, but rather holistic teaching competence. We utilize a we utilize a pedagogical model called to play, to think, to code, and to link. After mastering concepts in the gamification app, the teacher transitions to a more open block-based coding environment. In our example, we utilize a pre-built programs with bugs to decompose the logic and write their own code. So basically, we have created a custom build. It looks basically the same way as Scratch in a way, how to program, but we have created that in Unity. So after you finish the first part with NPCs, you are transported to that, and you can start testing all pre-built programs, how to solve them, how to solve their bugs and everything. So basically, we want to test their logic, not their programming skills, basically. So, and finally, they are tasked with linking these skills later to design a practical science lesson, solidifying CT as a cognitive tool. So, in conclusion, this methodology offers a comprehensive blueprint for modernizing CT and science teacher education. By moving away from rigid training methods and embracing adaptive gamification, AI NPCs, and learning analytics, we can significantly reduce cognitive load and foster genuine engagement. It is important to say that while the technology drives adaptation, the educator remains absolutely central in guiding the pedagogy. As our environment right now is currently in the alpha phase, which basically means we have mostly finished the application, and we're trying to finish the dashboard application. We can extract the data, but we haven't fully developed the dashboard of the learning analytics. So we're trying to make it more how the application in the tablet will show the data more like intuitively. So our next phase is we'll focus on after we finish the dashboard, to focus on the empirical validation to assess its impact on teacher self-efficacy. Thank you for your attention, and I will be happy to take any questions you want.
Great.